This is Sanjay Haresh, and I'll be presenting our work towards anomaly detection in dashcam videos. This is a joint work with Sateesh Kumar, Zeeshan Zia, and Quoc-Hui Tran. Smart dashcams are becoming increasingly ubiquitous. Many systems have been built which use dashcams to detect anomalies like lane departure and forward collisions. These systems also require special hardware such as radar and lidar to work properly. This method of detecting anomalies on the road, however, is cumbersome, as we need to build specific models for each kind of anomaly. Accidents, on the other hand, are long-tailed. That is, there is a large number of accidents that we cannot model. Therefore, we propose to explore data-driven methods to detect anomalies on the road. As an example, consider this clip. On the right, you can see the current frame in the clip, and on the left is the anomaly score predicted by our model. A model is able to detect anomalies without having to encode any rules. It has learned to detect anomalous driving patterns just by watching dashcam videos. There has been a lot of work on data-driven anomaly detection. However, most of the literature has focused on datasets in which the anomalies are based on visual artifacts. For instance, in UCSD pedestrian dataset, which is one of the most widely used anomaly detection dataset, merely the presence of a vehicle is considered to be an anomalous. Shanghai Tech is another dataset in which anomalous videos consist of objects which are not present in the normal videos. However, road accidents generally comprise of contextual anomalies, in the sense that objects in the scenes do not change. However, the nature of the interaction between objects changes significantly. Consider this sequence as an example. The objects here are not novel or anomalous. However, their interaction, that is the cars coming too close, deem it to be an anomalous scene. Previous datasets do not capture such example. Besides having simple visual anomalies, previous datasets for anomaly detection mostly consist of static viewpoints. UCSD pedestrian dataset consists of only 98 videos with static viewpoints. The normal scenes consist of pedestrians walking along a road, whereas anomalous examples consist of videos where moving objects such as vehicles and people on skateboards can be seen. Similarly, Shanghai Tech is also a very popular anomaly detection dataset. Shanghai Tech has more diverse scenes and is much larger. However, the camera is still static, and anomalous examples still consist of moving objects such as vehicles, bikes, and skateboards. On the other hand, UCF Crime is a huge dataset for real-world anomaly detection. The dataset consists of diverse, crowdsourced videos with complex anomalies including arrest, burglary, explosion, and so on. However, all videos are still from static viewpoints and not very relevant for road scenes because the dataset is aimed at surveillance use cases. The dataset proposed in the paper Anticipating Accidents in Dashcam Videos presented at ACCV 16 contains videos collected from Dashcam. However, these videos are still very small, with each being around 5 seconds long, and the accidents do not involve the ego car, which is more interesting to model in dashcam scenarios. Therefore, we propose a large and diverse dashcam video dataset called Retro Trucks. We collect 474 sequences from YouTube videos, where 254 are normal driving scenes and 220 are anomalous. Out of the 220 anomalous sequences, we label 56, which we use as our test set in the experiments. We ensure that our dataset has diverse driving conditions, including rural and urban traffic, various weather and lighting conditions. In addition to that, our anomalous examples include collisions, rollovers, and also near misses. Note that all anomalies involve the ego car. In our experiments, we use two classes of data-driven anomaly detection methods, including one-class classification and reconstruction-based methods. In one-class classification, we train a network to learn a manifold over the embeddings of examples shown during training, by constraining the manifold to be as small as possible. This ensures that the network is only able to embed examples that it has seen during training. At test time, any data point that is mapped outside of the manifold is classified as anomalous. Therefore, by training the network on only normal driving sequences, we can get a network that can detect accidents because it has never seen any accident at training time. We use an I3D as our backbone network. We note that most anomalies in the real world are not due to appearance of novel objects, as encouraged by previous datasets, but they are due to novel interaction of already known objects. Therefore, we seek to infuse object-object interaction priors in our network. We use state-of-the-art region proposal network to report regions of objects in the individual frames of the video sequences. Given the object bounding boxes, we use ROI align to extract features from each region. We then build a similarity graph over the features of objects, which is then fed to a graph convolutional network. The features from GCN are then concatenated with the features from the encoder before feeding it to one-class classification loss. The hope is that by giving this network strong priors in the form of interaction graph over time, it should learn normal interaction modes. This should help distinguish between object interaction in normals and anomalous sequences. We train an I3D and a variant with GCN as shown before with one-class classification loss on UCSD pedestrians 1, Shanghai Tech, and Metro Trucks. We note that although we could not achieve great results with one-class objective, it is still very evident that modeling object interaction does help over the baseline I3D. Reconstruction-based approaches learn to reconstruction through a bottleneck representation. Intuitively, they learn to reliably reconstruct the data shown at training time, and poor reconstruction of inputs at test time is used as a cue to detect anomalies. We devise a 3D autoencoder to reconstruct video clips of 32 frames each. The autoencoder consists of two networks, encoder and decoder. The encoder network takes as input video clips of 32 frames and generates a bottleneck embedding of the clip. This embedding is then fed into the decoder, which learns to reconstruct the input. We train the network exclusively on normal examples in the dataset. Since the network is crippled by a bottleneck layer, it can only learn to reliably reconstruct the normal examples. The network, when fed with anomalous examples which it has never seen during training, such as accidents, fails to reconstruct the examples with high enough fidelity. This leads to a spike in reconstruction error, which is then used to detect accidents. We also use the same idea of object interaction with reconstruction networks as well. In this case, the features from both the encoder and the GCN are concatenated before the decoder takes them as input and reconstructs the input clip. We achieve a decent performance with the highest AUC of 0.715 with I3D plus GCN. We note that previous methods do not achieve as high performance as on other datasets, showing that RetroDrux is much harder to do to moving camera and contextual anomalies. Next, we show some qualitative results of our best performing model. As we can see, our network is able to detect multiple accidents in one video clip. It is also not limited by diverse viewpoints. And it can also detect collisions, even when it mostly occurs off camera. Next, we show some failure cases of reconstruction-based approach. As we can see here, the network picks on the movement of Viper as an anomaly and assigns it a higher anomaly score than the actual accident that occurs in the sequence. This problem with reconstruction-based approaches is due to visual anomalies. As it is, objects that do not occur in training set heavily affect the reconstruction score of these networks. Therefore, they fail in scenarios where visual anomalies occur along with contextual anomalies. Thank you for your attention.